Liquid Nitrogen by Keara and Miles.
For our experiment, we decided to make ice cream using liquid nitrogen and explore the science behind not only ice cream, but liquid nitrogen as well. We needed a few materials in order to make our experiment successful. Most of them were easy to find in the store at home. We needed gloves, a large metal bowl, long-handled wooden spoon, and our ingredients, which consisted of milk, half and half, sugar, vanilla, and you can't forget the most important ingredient, liquid nitrogen. Gloves and goggles had to be worn at all times in order to avoid freezing our skin at dangerous temperatures. Here we see Miles pouring in the milk, which will act as the fat in the ice cream. We'll learn about what that does later.
Here we see Keara adding cups of sugar to the ice cream mix. The sugar will add to the ice cream's overall sweetness and also add to the structure of the ice cream, as you'll learn about later.
As you already saw, we mixed all of our ingredients in a large steel bowl. At this point, you can really add anything you like. You can replace vanilla with any flavor you want. You can add chocolate chips, sprinkles, or fruit, whatever sounds good to you. Make sure you have your glasses and goggles on to ensure that if the liquid nitrogen touches you, it won't burn your skin. Don't stir the mixture right when the liquid nitrogen touches the liquid base. Let the liquid nitrogen do its job of partially freezing the mixture. If you stir too soon, the concoction will bubble over and you'll have a mess, and you'll waste some of your delicious ice cream. Stir the mixture with the wooden spoon once the liquid nitrogen has settled for a little. Some of the cream will be completely frozen, while other parts will still be liquid. Keep stirring until you have a consistent mixture all throughout, and then add more liquid nitrogen. Let it freeze for a few seconds before stirring again. Stir, 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 and stir more until you have a consistent mixture. And keep adding small amounts of liquid nitrogen until you have your desired consistency.
The vapor you see coming out of the mixture is actually nitrogen gas. The liquid nitrogen has to be kept at such a cold temperature in between negative 210 degrees Celsius and negative 195 degrees Celsius that any time it comes into contact with something warmer than itself, which could be the bowl or the atmosphere, really anything, it turns immediately, or it vaporizes immediately into gas. This is also why we don't have any leftover nitrogen in our ice cream at the end when it's finished. It all evaporates out into the atmosphere.
Here are some tunes to keep you occupied while the liquid nitrogen works on making our ice cream as freezing as possible.
Do you remember 21st night, September? Love was changing the minds, pretender, while chasing the clouds away. Our hearts would ringing in the key that our souls would singing as we danced in the night. Remember how the stars stole the night away. Oh yeah.
And now you can see our final product.
It's actually really good.
Wait, Elliot, come here. You're getting interviewed.
This is actually really good.
You like it more than Hardigan.
Whoa.
Come here.
Which one?
You. So what are your thoughts on the ice cream?
I think it's wonderful. It's delicious and perfectly cold.
Ah.
That makes no sense.
Sprinkles.
Put the rest of it on one cup.
Okay, verdict?
Yo, you could keep your cups and spoons if you want seconds.
It's mad decent.
Mad decent.
That's my
for
verdict.
Mad
Decent.
Liquid nitrogen was first liquefied by two Polish physicists by the names of Zygmunt Wroblewski and Karol Oleski in 1833 at a Polish research university. Nitrogen is a colorless and tasteless liquid that has a density of 0.807 grams per milliliter at its boiling point, which is negative 195.79 degrees Celsius. Very cold. Nitrogen can be a liquid between the temperatures of negative 210 degrees Celsius to negative 195 degrees Celsius, which was the temperature that was maintained in the dewar that held our liquid nitrogen. It is not produced the same way as it was by our friends Zygmunt Wroblewski and Karol Oleski. Nowadays, people produce it industrially by harnessing the method of fractionally distilling liquid air, or in other words, separating a liquid mixture into fractions based on differing boiling points by means of distillation and typically using a fraction column. Cryo is a prefix that means involving or producing freezing temperatures, so cryo is a perfect fit for freezing temperature of liquid nitrogen. Cryogenic is defined as causing rapid freezing on contact with living tissue, hence why we had to wear gloves at all points in the lab dealing with liquid nitrogen. Liquid nitrogen is useful for cooling things very quickly, explaining why it made our delicious ice cream so rapidly. As we saw in the experiment, nitrogen went through a phase change from a liquid to a gas, which is called vaporization. As shown in the phase diagram on the right, temperature is always on the x-axis and pressure is always on the y-axis. You can recognize the presence of the different phases because there is an obvious boundary between them on the phase diagram. You can see a boundary between the solid nitrogen and the liquid nitrogen. In order to keep recognizing these boundaries, phase diagrams are here to help. As we see on the boundary between solid and liquid, there is a point at negative 209.86 degrees Celsius. This is the melting point, because as nitrogen is shifting from a solid to a liquid, it is melting. Now we look on the phase diagram again, and we see a boundary between liquid and gas, and there's a point at negative 195.8 degrees Celsius, which is the boiling point. This explains why it's useful for cooling things very quickly, but not for long periods of time, because it immediately evaporates when it comes into contact with anything warmer than itself because of its extremely low boiling point.
So, here we go with the science behind the freeze. So, we've told you that liquid nitrogen makes great ice cream, and you've heard it yourself. But now we're going to delve into exactly why it makes such good ice cream. So, as mentioned before, liquid nitrogen is a cryogenic fluid, which, as you were told, means it can freeze things extremely quickly, and the quicker the freeze, the smoother the ice cream. But that still doesn't really tell you much. To understand why a quick freeze makes better tasting ice cream, we first have to break down what ice cream is really made of, including the ingredients a lot of people do not know about or are not able to see, along with the actual process itself.
Ice cream is mainly made from ice crystals, fat, and air. The ice crystals are formed when the liquid or watery base starts to freeze due to the extremely cold temperatures it's put in. The ice crystals determine the texture of how fine or grainy the ice cream will turn out. The next ingredient of the ice cream is fat. The fat comes from the milk base and the fat that is within the milk. The fat makes the ice cream rich in taste and gives it the dense, creamy structure we love. The sweeteners, such as sugar, which are the best part of the ice cream, add the sweet taste. The last ingredient is the free one. It's air. Air cells are whipped into the base of the ice cream. The fats and air work together to give the perfect consistency of ice cream. Hence why ice cream is sometimes described as airy.
Now that we've gotten the ingredients down, let's look at the combination of all the ingredients. The base of the ice cream, in this case the milk, cream, sugar, and vanilla, all need to come together to form the actual ice cream. But how does it do it? Under normal circumstances, as most would guess, the mixture doesn't just combine. But with the help of an emulsifier, we are able to combine the elements to create our treat. In this case, the emulsifier is the liquid nitrogen. And just a quick side note, essentially what emulsion is the process of combining two or more liquids that under normal circumstances would not be combinable. A stabilizer can also be added to the mix, which is just there to prevent the ice cream from melting quickly. In most cases, this would be some sort of gelatin mix, but for our recipe, we left that ingredient out.
Besides air, there are two main ingredients that determine how good an ice cream will taste. These ingredients are ice crystals and fat globules. In this context, we will focus mainly on ice crystals. They pertain more to chemistry than do fat globules, which are more related to biology. Crystallization will be the main focus of the rest of the presentation.
Moving on to ice crystals. As we mentioned earlier, those ice crystals play an important role in the creation of ice cream. They ultimately decide how smooth or grainy the finished product will be, and that can be crucial to the taste. Liquid nitrogen is considered one of the best ways to make ice cream because of how fast it can freeze the liquid being the dairy products and the water in them, in the base of the ice cream. The slower the freeze, the larger the crystals. Because it's such a rapid freeze, the crystals have no real time to form, making them extremely small, which in turn gives the ice cream a very smooth texture. This fast freeze will also be explained later in the presentation.
Now moving on to crystallization, which is a critical factor in ice cream because the crystals allow the dessert to be in between a solid and a fluid. Crystallization is defined as the organization of molecules into a solid phase within a fluid. Crystallization can occur in 4 stages: nucleation, growth, recrystallization, and supercooling. To end our presentation, we'll go over each of these 4 stages of crystallization, arguably the most important part of the ice cream making process besides eating it.
The first step of crystallization is supercooling. Supercooling occurs when the temperature of a liquid drops below its freezing point. This allows for the molecules to form into clusters. Generally speaking, water molecules are continually coming together to form clusters held together by hydrogen bonds. At the same time, those same clusters are breaking apart due to molecular vibrations. The lowering of the temperature, though, greatly enhances the cluster formation rate. The second step of crystallization is nucleation. The nucleation process starts with the initial cluster of ice as a loose aggregation of molecules. As the cluster starts to lose energy, a lattice structure begins to form and the cluster becomes an embryo. When the embryo grows large enough to be in thermodynamic equilibrium with the solution, and when the embryo overcomes the energy barrier to nucleation, it is a nucleus, the smallest collection of molecules in a crystal lattice that will not redissolve. When the nucleus grows, it will grow into a crystal. The third step of crystallization is growth. The growth aspect of crystallization is a bit more complicated and out of the scope of this class, so it will be briefly summed up. Growth is essentially the part of the process where the crystal structures form. Depending on a multitude of factors, the pattern of growth for crystals can vary. Although, an important note is that slower freezing causes fewer nuclei to form per given volume and time, which ultimately allows more space for each crystal to grow in, which results in larger crystals. This explains why a faster freeze results in smoother tasting ice cream. The fourth and final step of crystallization is recrystallization. Recrystallization is another topic that is a little more complicated and outside the scope of our class, but summed up, it can be described as the changing in shape and size of an individual crystals while the total mass of the crystal remains constant. Essentially, it's just the final changes of the crystals forming into their final shape.
Shown below is a microscopic picture of ice cream. The arrows point to ice crystals, air bubbles, and the sugar solution.
Also, an interesting side note, ice crystals range in size from about 1 to over 150 micrometers squared in diameter, with an average size of about 35 micrometers squared. And just real quick, a micrometer squared is 1/1,000,000th of a meter. That's incredibly small.
We hope
Hope
you
you
enjoyed
enjoyed
this
this
presentation
presentation.
and our ice cream if you were lucky enough to get some.
Hopefully you guys learned a lot about the science behind what makes ice cream, and we wish you good luck if you ever have the chance to make some.
Ice cream, you
You
scream,
scream,
we all scream for liquid nitrogen ice cream.